Everyone, pleasure to be here. So as mentioned, I'm Yair. I've been actively involved in security for the past 15 years in a variety of constellations, and actually most of the years have been in the field of web application security, so OWASP is very close to my heart. I've been the lead researcher of Watchfire. Later on, while we were acquired by IBM, I took the role of managing the application security group of IBM. But in the past 4 years, I've been focused on mobile security. SkyQ, the company I co-founded, is focused on mobile threat defense, and we do a lot of research around the landscape of threats, network attacks, malware, and vulnerabilities. But today I'm going to be focused on malware. And in very short, what I'm going to do today is quickly discuss the evolution of mobile malware with a few interesting trends we're seeing. Later on, I'm going to discuss a way to actually break app-sandboxing in Android without rooting the device. It's recent research we've conducted. Later on, we will be discussing the variety of techniques in which security technologies are able to try to analyze apps to identify if they are malicious or not. And we will obviously discuss the shortcomings, the inherent shortcomings of these approaches. And I'll conclude by actually creating a demo on stage that will show how these limitations can be used by malware authors in order to bypass detection. So let's start. I want to start with this, the ping pong virus. This is, I believe, the first virus I saw as a child in '88. Who remember that virus, by the way? Okay, that's a sign you're old. So the interesting part is that if you actually think about what happened since then to today, I'll fast forward, we've moved from a situation where there was an inconvenience conducted by these kind of viruses. It wasn't really bad, right? It was just annoying. But if you look like 25 years later, we were seeing more and more attacks like Sony, like Target, like eBay, like Yahoo just recently. That target organizations using the same kind of concept, but that's the time for really bad ramifications. Actually, if you really think about what's going on today in the world, this is used by nations to attack each other, right? Think about Stuxnet, think about that event. About a year ago, we've seen infrastructure being taken down by Russia against Ukraine. And this is the level of attack we're seeing today in the computers and networks world. But my point is that the same kind of evolution is actually happening very, very, very fast in the field of mobile malware, and for obvious reasons, right? It started by adware, by annoying apps that were annoying us as consumers, but very quickly we've been seeing attacks against two-factor authentication. Attacking the mobile device meant that you could steal the password, but also the other mechanism like SMS. And we've been seeing more and more attacks like spyware recently in our customer base and also publicly. And these kind of attacks are affecting organizations, but they're also affecting countries. So who heard about Pegasus, for example? Can you raise your hands? Okay. So Pegasus is a recently uncovered tool that was actually sold by NSO Group for a few years now. And that tool did the following, just what you see in the screen. What it did is allowed organizations or nations to just compromise iOS devices, Android devices, and Blackberries. And the motivation was not only about stealing the data you have on your device, the chats, and this access to other services that you have, which is the definition of compromising any computer. It also used something that is very unique for mobility, and in my eyes is an amazing asset by attackers today. By compromising a device, an attacker can actually snoop on where we go, who we meet with, why we meet with him, and also listen to what we say when we are sure nobody's listening, right? And we still believe that nobody's listening, but it's actually not very hard to mount these kind of attacks. It's not yet formalized, but I just read 2 weeks ago that the FBI is investigating and possible attack on democratic representatives in the USA on the mobile devices. So this is something we start to see more and more and more. And I want to talk about the challenges of attackers, as well as what we see attackers are doing in order to overcome them. So there are two main things that I believe are very good in the way mobile operating systems were built, in the way we consume apps. First one is that today, most apps are consumed from public stores. And these stores, Apple and Google, they are reviewing them and they're improving their review process all the time. That makes a challenge for attackers to either get through the app stores or maybe try to get through other forms, and we will discuss this. The second element is that we are getting used more and more to do certain things when we install apps. That's good from some aspects, but it's also bad from other aspects, and we will see what attackers are doing to utilize that. Okay, so I chose a few incidents from the past year. It's not conclusive in any way, but I believe it represents an interesting examples of what's going on. So how many of you have heard about XcodeGhost? Okay, so it's actually an amazing kind of attack. The point there was that attackers decided to create a repackaged version of Xcode, right? The IDE for developing iOS apps. They created it and they actually distributed it through Baidu. And many developers, including the WeChat developers, which is actually an extremely popular chatting app used by hundreds of millions of users, downloaded that repackaged version of Xcode. The point was that it was still the same IDE working well, generating new apps, but it was also injecting malicious code to any application that was generated using this IDE. The end result was actually pretty amazing. Legitimate, trusted developers have published to their public store of Apple new versions that seem to be all right, but they actually included malicious logic, right? Apple trusted these developers because they were benign developers and didn't identify that malicious code that was injected to all of these apps. The end result is that millions of legitimate iOS users got infected by that malware. And we actually still see people infected by that malware, even though it was identified far away from now. Another example is eSpectre. It was actually identified shortly after XcodeGhost. Another campaign, and in this case, the idea was completely different. Again, like XcodeGhost, it affected non-jailbroken iOS devices. But this time, the distribution method was actually using enterprise provisioning profiles. This is a technique used by organizations to deploy internally developed app without being reviewed by Apple. Again, a very useful capability, but in this case, it was used to actually distribute these apps to anyone that was lured into installing them. And we've seen very interesting patterns of attacks, like in the Far East, we've seen manipulation of traffic in order to lure people to actually install these apps. So again, a lot of people got compromised. But in this case, since these kind of attacks were not using the App Store, they could use much more aggressive APIs. It is called private APIs. And for that reason, this kind of malware was much more aggressive. It was able to silently install apps and hide it from you. It was able to remove apps that they didn't want you to use, and many other very powerful capabilities. If we jump to Android for a moment, in the past 5 years, we've actually seen a very interesting trend that is interesting not only from a security perspective. What happened is that like 5 years ago, as you may remember, Google Play was riddled with a lot of malware. And at that point, Google have decided to develop a variety of capabilities that were intended to actually monitor the store, the submission process, and do it much more similar to Apple. And over the years, Google Play has become much clearer in terms of malware. They still have. I see on a weekly basis new reports about malware in Google Play, but it's much cleaner, okay? And that has led to two aspects I'm going to discuss in this presentation. First one, it made attackers have to move from Google Play to third-party sources that are today riddled by malware. So we've seen phenomena like repackaged apps, which I'm going to discuss later on, but we actually saw these kind of apps becoming more and more aggressive. So let's take an example of something we did in SkyQ recently, and I believe it will be an interesting example for the kind of things that are starting to influence the Android malware ecosystem. So what I'm going to show you is the process that we took in order to try to be able to actually circumvent app-sandboxing, which is an inherent capability of the operating system, without rooting the device. So very quickly, what I'm talking about when I'm saying app-sandboxing is a concept that made mobility so widespread and easy to use. The concept that says that unlike, I don't know, Windows, when you install an app, it's actually limited. It is intended to influence itself and some limited ecosystem. It shouldn't be able to influence other apps. It shouldn't be able to influence the operating system. And that's the reason why you feel comfortable downloading a game and using your corporate apps and using your bank on the same device. Very important mechanism. So what we did pretty quickly is start to think about mechanisms that might be able to allow us to do interesting stuff. And obviously we came very quickly to accessibility APIs. APIs intended to make people that are, for example, visually impaired, more easily use the device. So over the years, you may remember that these mechanisms were used in Windows and iOS to actually circumvent a lot of security models over the years. But we started and looked on Android. And when it comes to Android, this accessibility framework is actually extremely powerful, okay? This framework, by the way, how many people use Android in here? Okay, so you know it, right? It can allow you, for example, to install an accessibility app, which will read for you what happens on your device. Think about it. That means that there is a way to actually be able to look on what's happening on a device. It's actually much more stronger because it allows this app that has these permissions to actually perform actions for you on other apps. So logically, that's actually compromising the notion of app-sandboxing as a feature in the operating system. But when we looked at it, it was very clear that the developers of Android were aware of this exposure. And for that reason, they've created a process that is extremely cumbersome to allow an app to get these permissions. I want to show you how it looks like. So as a user, if I want to give permissions to use accessibility to a given app, I have to go through all of these steps, many clicks. As you'll see, a variety of warnings that the attacker cannot control. And as a result, we've never seen widespread malware using these capabilities because, seriously, most people would just stop in the middle. It looks fishy. It's not something that we're used to do. So most people would click cancel. So we continued to think about how can we still get to use this capability without having the victim do all of that, because it's not realistic. We want to have widespread malware. So we got to this following technique, which we called accessibility click checking. It's actually a reference to click checking in the field of web, Jeremiah and Arsnake. And it's a reference because the right term would have been accessibility tap checking. It was just a gesture to those guys. So the technique was the following. We looked at a different kind of capability that we have in Android, and this is the draw over apps, commonly known as the cool feature that Facebook used to actually be able to put your faces on the screen when you get messages in Facebook. And the idea in this is that there are two features, two capabilities in this draw over apps capability. First one is the ability to actually draw your own UI over any other app whenever you want to do it. But that's not enough. The second flag that can be used is actually a flag not focusable, which means that if someone clicks on the overlay will not get the click. It will actually propagate it to the next level of the UI. So now connect all of that together, and you will understand there is actually an inherent feature, set of features in Android that can allow to do pretty bad stuff, right? So let's see this in action. I want to be very clear. I'm showing you a game we've created. We are not a game company, so please don't laugh at the UI. But I want to show you this as a POC of accessibility click checking. So in this case, we are playing a Rick and Morty game. And the idea is that we have to just click on misX that show on the screen, right? It's like kicking a rat. Okay, so we clicked 3 times. We are very happy. Did anyone see the accessibility permissions dialog, this annoying dialog that makes us afraid? No, right? But what actually happened in the background is that while you were playing, we just loaded in the background the accessibility permissions dialog, and each click that you clicked was actually approving these capabilities. So now this cute app that you see on the screen has the capability to do some very bad stuff. So let's see an example. We're going to open Gmail. Just to be clear, Gmail is a well-written app using all the classical capabilities. And the demo I'm showing is actually applicable to any app that we are aware of. Secure containers, banks, emails, whatever. And in this case, what I'm doing is actually sending an email to my CEO, and everything looks benign. I'm trusting app-sandboxing, right? Shouldn't be concerned. But as you may guess, what's going on in here is that this cute game is no longer a game now. And what we can see here is actually every type that we've done over Gmail was recorded, even the things that I wrote and then deleted. I can see it as a malware. So what we're seeing in here is another example where I just opened the app again, and without me knowing about it, now this malicious app has the admin permissions. So in this case, what I demonstrated is the fact that once the malicious app got the accessibility permissions, it can snoop around all other apps, but also take actions on the victim's behalf on those apps. Okay, so those of you that looked into the demo may have noticed that this was Android 4. And yes, when we first found it and published it, it was perceived as a problem that applied for Android 2 to 4. Why? Because in Android 5, they've introduced another mechanism, and the idea was that for critical buttons in the OS, like the final OK button for approving this dialog, there is no way for an overlay to propagate clicks. Okay? So it was perceived as impossible to create accessibility click checking attacks, because you have to have the OK button visible to the user in order to be able to click on it. But that's obviously a very weak mechanism, as we've demonstrated publicly. What we did is actually create the same attack exactly, but in this case, in the last phrase, what we do is actually create a hole in the eye, in this face, and this hole is actually directly exposing the OK button, the last button in the process. But the victim has no way to know that, right? So this is a very easy mitigation for that protection. So this was the first part of the presentation, just a few things we're seeing, and this is actually a very concerning trend, as Google has identified what I've just shown you as a problematic bad side of a very important set of features, and they are not planning to fix it till 5. Starting 6, there are a variety of additional mitigations that make it less effective. In Android 7, I know that they've been investing in more and more protections for that. But again, there is more than 80% of people today that are easily susceptible to that. So let's jump over to discussing a few concepts, right, for analyzing apps. Signatures, obviously, static analysis and dynamic analysis. And we will discuss all of them in the next couple of minutes. So about signatures, there is no much to be said, right? It's a 30 years old concept, still widely used. But in this case, someone has to flag a given app as malicious, create a signature for that. And it is generally a pretty accurate technique because someone has decided to flag someone as bad. Obviously, the dark side of that approach, which is widely used, is that by manipulating a given malicious app, the signature can be bypassed. so it's not perceived as a very sophisticated approach. More sophisticated approach is obviously doing some dynamic analysis. And in this case, the concept is obviously creating an environment and just running the app in it, and then monitor everything we can monitor in order to deduce something is bad, right? The actions it does, if it's trying to exploit the environment, if it's trying to communicate to bad servers, etc. A pretty cool technique, but the problem with it is the definition of trying to run something and analyze it, right? You are bound to learning only about what actually is being executed, right? And that's the problem that attackers are using in order to try to bypass these concepts, these technologies. Just a few examples. Time bombs just saw an app that actually implemented many of these techniques that was waiting for some time before it started to do some malicious stuff. And sandboxes usually have a limited time to analyze an app, so by just waiting, it was bypassing the analysis. Another approaches we see sometimes is that the app waits for an action to happen on the device, an action that happens on real devices. Another thing that we see is IP bombs. An app can, for example, look if it's running in Amazon. If it does run in Amazon, maybe it will not run the malicious logic. So the sandbox can decide to maybe just fake the APIs for checking the IP to provide a false IP. But obviously the malicious app can decide, instead of using the APIs, just to send a request to the internet and check what was the real IP of the machine. So it's a never-ending game of bypassing each other. The last thing that we see happening more and more is, as I mentioned, just waiting and trying to analyze if there is a real user using a real device on the device, right? So in some cases, the malicious logic happens only in the third level of the game and stuff like that. Things that make sure that a real person is using the device. Sometimes we see apps that check the contact list and a variety of things that indicate only a real user. So this is about dynamic analysis. When it comes to static analysis, the idea is obviously taking an app and statically analyzing it to identify if something fishy is going on. And the main advantage of that is that the app is not really running. It's an advantage and a disadvantage, but the attacker has much less to do in order to control the analysis. Let's talk about one of the core techniques in static analysis. It is named Taint analysis and actually used most notably also in application security, in analyzing apps for vulnerabilities, but also for identifying if they are malicious. And the notion about taint analysis is trying to model an app, model a function, and be able to just analyze how data propagates, right? So in this example on my screen, what we can see is that there is a method that gets sensitive information into the data parameter. Then it gets some manipulation, but propagates into data 2. And then we see a post request that actually sends the information outside of the device. So obviously, the idea is that we call the first method, the get sensitive data, as a source. It's a method we don't want to propagate outside of the device, right? And the method of, let's say, posting the request is a sink. It's something that we don't want to contain sensitive information. So by analyzing the flow, we can identify if something bad is going on. But I want to highlight that this concept is actually a very problematic concept because it has an interesting trade-off of false positives and false negatives. And I want to give you an example for that. So let's say that we look at the app and we have identified a variety of sources, a variety of functions that contain sensitive information, and we've identified a variety of sinks. In this case, we do an analysis and we see there is a connection between a source and a sink. So that's bad. And that's simple. But what about the following scenario? Let's say that the information propagates into an array, right? And we see that some cell of the array then is used in order to get into a sink. But since we look at the app statically, we cannot know if maybe the sensitive data gets to the first cell of the array, but later on, the third array is used in order to get into the sink. So in this case, this is obviously not an issue. But we have to decide if we will decide that there is a connection or not, even though we don't know. So it's a trade-off, a very tricky trade-off. And that's why static analysis solutions are known as problematic in that sense. They either lose identifications or they just flag stuff that is not correct as a problem. Let's see another example, a very simple example, and there are ways to solve that, but it's a simple, very clear indication of the challenge of analysis, right? An app can decide to have this following code. We have data that contains sensitive data, and then we have a quick for that actually practically copies the data from data to data 2, but you don't have a direct assignment from data to data 2. So again, as an automatic code, you may be missing the clear leakage of information. The other approach is obviously just using dynamic code, right? So let's think about two examples. So first one is actually something that has been around for a while now. I haven't seen enough noise about it, but if you think about hybrid apps in app stores, like think about PhoneGap and many, many other infrastructures. By design, it's an app. It gets to the store. Apple or Google can analyze it. But by design, you have an embedded browser. You have HTML dynamically loaded when you use the app. It can change from today to tomorrow, right? And it has a bridge. It can invoke native capabilities. So it's by design a very effective way to either bypass static analysis, but also bypass the monitoring of the big vendors. The second example, which we will see in more detail in a few slides, is just dynamically load code. So think about the notion of having an Android app. It calls for a function, okay, for an internet URL. It gets back in the response in your URL, dynamically URL. Then it loads that URL, downloads it, and dynamically loads the code. So when you look at the code statically, you have no way to know where is this new code and whether it is good or bad, because it looks like a generic extensions logic, right? Dynamically loading code and running it. So it's two inherent limitations. And I think if I have to summarize the analysis on dynamic and static limitations, there is a generic way to create an app that will easily bypass classical approaches of static and dynamic and signatures. And the idea in this case would be to make sure that when a given app is analyzed by a sandbox or an analyzer, it will get benign code, but when it actually gets to our targets, it will load and run bad code. And I want to give you a live example of that. I want to try to build on stage this kind of malicious app, okay? And I want to connect you to something I mentioned earlier in this presentation, right? We talked about the notion of having less and less apps, malicious apps in Google Play, and that malicious authors are forced to get into third-party sources. But this trend actually created a problem to malware authors. It's the problem of exposure. Google Play has a lot of users, third-party stores have less. And for that reason, we started to see more and more malicious apps that are using the concept of repackaged apps. Instead of just creating yet another flashlight, malicious flashlight, they just take popular apps, unpack them, and create a new version that looks exactly the same, but is also malicious. And we recently saw a lot of campaigns around Pokemon Go, which became extremely popular, where people would just create a fake version of Pokemon Go. It behaves the same, but it's also malicious, and many, many people have downloaded it. So let's start. So what I'm going to do now is just do a step-by-step quick demo of what I described, and I'm going to create an extension-like mechanism that will be used for the demonstration. So the first thing we're going to do is generate keys that will be used by us in order to re-sign the app later on. The second thing we're going to do is to actually unpack the app. But let's talk about the app that we're going to use for this demonstration. It's a small and very, very addictive game named AA. So I want to show you that I know to play it very, very well, at least the first stage. And it's a very quick and nice game, okay? So I just used the public available version of that game, and I'm going to uninstall it from my device, okay? Now I'm going to unpack the APK, and what we are going to use is actually APK tool, a public open source solution that will actually unpack the APK into the resources and the code and everything. So let's take a quick look at what we have. First thing we're going to look at is the areas where we would like to do some manipulations to the app. So we're looking at the manifest file, and we're going to later on add some permissions to the new version of the app. But we also want to know what is the entry point to the app. In this case, we see that this is the base activity. So let's take a quick look. And what I'm going to do is actually open the Smalley version of the app. It's the intermediate code, base activity. And I'm looking for the onCreate method, which is the method that is called when the app is loaded. So the idea is that we want to maybe inject a new method into here and just make sure it is called whenever the new version of AA will be used. So for that, I'm going to use a Python script we've created that is actually able to inject in a variety of ways code into an unpacked version of an APK. And in this case, what we can see is that we've added a bunch of permissions, and we can also see a new version of the base activity, where we have a new method called win0 that will now, just when being run, download an APK from a server and dynamically load it. Looks like an extension-like process. The next thing we want to do is actually build back the APK. And while we're building it, which takes some time, I want to show you another thing. In this case, I'm creating a new APK, and we want this APK to run dynamically when the new AA version will be loaded. So we are now building this new version. And in the meanwhile, we will also just sign and align the new APK to be able to be run by a new Android device. So we just finished. We have a new APK that is the new version of AA, and we also have an APK that we want to dynamically load when the app is being run. So let's see this happening. I'm setting up a server that will load the dynamically loaded APK, and I'm installing the new AA game back into the device. So what we can see is that now we see the same app, but we see the new logic that is not malicious, loaded and running in the app, and we can see that the APK was loaded from the server. The app still works as before. The interesting part gets now. Let's say that we waited a bit, the app was analyzed, and we now want to actually attack our victims. So we can have another version of the APK, looks the same, but in this case, this APK, when run, will actually start to snoop on the device and look for the last calls, the meetings, the contacts, very simple Java code. So now we're going to get to the server the new version of the APK. And let's see what happens when I'm just using the game a day later. For me, it looks the same. You can play it. But as you can see on the server side, we can see the contacts, the last calls, information leaked from the device, and actually allows us to attack the attacker without changing the actual malicious app in any way. Okay, so I hope it illustrates the problem here, right? Static, dynamic, and signatures will likely miss this kind of malware.
Is there no warning about downloading and executing the APK or normal step-in process?
So this is an APK that you can just put in, you can try and get it into Google Play, that's okay, but you can also use and put it in any other source, like a third-party source. So when you download it, it will look exactly the same as any third-party source installation. Okay, so if you look at what I just did, there is one limitation, one thing that security software can certainly do in order to detect this kind of malware. And that's the fact that in this case, there is a command and control server that the app interacts with, right? You can blacklist it, you can do a bunch of things. What I want to introduce is just a concept. I have yet seen it live, but I would expect to see it happening much more. And that's the notion of, instead of using your own CNC server as an attacker, you may try to use social networks, legitimate services, in order to try to introduce your dynamically malicious code from there. So think about the notion of creating a Facebook user, okay, and just publishing whatever you want to publish in public posts. But when you want malicious logic to be loaded for your victims, you can start to just post encoded posts that embed a malicious APK, right? And by doing so, it becomes much harder to actually blacklist anything because it's a public, legitimate service. So it's something I would expect to see more. Before we conclude, I want to just share a few thoughts about what can be done, because my presentation is actually pretty dark, right? I'm just saying what's wrong in the world and what's wrong with solutions. So just to be clear, signatures, static analysis, and dynamic analysis are amazing technologies that are identifying in the field a huge amount of malicious apps and a huge amount of security vulnerabilities. What I'm saying is that there can be done more, especially in mobility. And the point here is that, in my eyes, analyzing only the app itself, looking at it statically, dynamically, is actually a mistake, because you can think about attacks in mobility as a flow, right? The bad APK or the bad app is just the end of it. And we believe that by analyzing and looking at other aspects like the developers, the reputation of the developer, where did the app came from, is actually extremely valuable. For that reason, we really believe in the notion of crowd wisdom, of using the fact that we have millions of apps analyzed, and we see how apps behave over time in order to identify things that are very hard to be done using static and dynamic. And I can share that this is a technique that is extremely valuable to expanding the exposure. It's not a one magical solution, it just complements the full capability of identifying malware. This slide is obviously very funny in my eyes, recommendation. So at the end of the day, I believe that most of what is written here is obvious to you guys, but as a fact, when we see the reality, we see a huge amount of successful attacks happening. So my point is that there are a variety of things that can mitigate the risk, right? Trying to download apps from the public store is safer than from a third-party source. Educating employees and colleagues to understand that these very useful devices are computers and should be much more careful with is critical as well. Other aspects that I believe are worth thinking about are trying to disable USB debugging, for example, from devices that are not used for development, as this technique is actually very useful from transferring malware from your PC to your mobile devices, and we've seen this happening in the past. And the last element is that at the end of the day, when we look at OS, we see a huge amount of vulnerabilities being fixed. I think that last year, 2015, was a record year where only for iOS there were more than one vulnerability identified and fixed per day. It was around 380. And these fixes obviously make the OS safer from exploitation, but also safer in terms of the design of the operating systems. And if I had to conclude, we've discussed today the problem of mobile malware, but I believe that when you think about security of mobile devices, you should understand that the threat landscape is actually much wider. We're seeing a lot of attacks against mobile devices through network interfaces. These mobile devices are connected almost 24/7 to a network, and we see a lot of attacks that target the data on your device or even compromise the device through networks around you. The same applies about vulnerabilities. Many of these vulnerabilities are obviously the fuel for many of the more sophisticated attacks. Pegasus relied on 3 core vulnerabilities fixed in 9.3.5 in iOS that allowed an amazingly effective compromise and jailbreaking of the device. From an enterprise perspective, I believe it's important to understand that there are tools that do the same thing that IPS, IDS, firewall, antiviruses have done for us for PCs, and they are readily available in the market. Guys, thank you so much for your time. I hope you found the presentation interesting. And in case you have any questions now or later, you're invited to ask. Thank you. Thanks. Yeah. Hi.
I do have a question about the dynamic analysis. So how is code you can't do and
For mobile?
how do you do that?
Sure. So you cannot do it. You cannot do it on the device. But what you can do is actually take the app device, upload it